Hi, I'm Curtis Skinner. I've been with Hy-Pro Filtration about 9 years now. I'm a regional sales manager and have a little over 25 years of experience in the fluid power industry.
Hello there. My name is Richard Trent. I'm a regional sales manager for Hy-Pro Filtration. Been with Hy-Pro for a little over 16 years. Prior to that, about 20 years in the fluid power industry.
Hi, my name is Scott Howard. I've been at Hy-Pro this is my 18th year. I'm a strategic account manager, and this is the Hy-Pro podcast. You see this fluid in a lot of power plants, but we see this in other areas as well. A hydraulic fluid that is fire resistant, phosphate ester. Any thoughts on that? This is an important fluid that I think we should talk about.
It is a fire resistant fluid. It's the predominant fluid used in power plant electro-hydraulic control, or also known as EHC systems. It has some unique properties, and you really need to pay attention to just a couple of variables in oil analysis. And if you do that, it's a pretty easy fluid to manage. But if you don't do that, it can get in an upset condition really fast and cost a whole lot of money.
So you're alluding to there's more issues than just dirt and water.
Correct. First of all, understand that phosphate ester is a group 5. It's a synthetic fluid. And like most group 5 fluids, especially the fire resistant group 5 fluids, they're very hygroscopic, which means they love water, simply stated. They pull water out of the atmosphere. When water gets into this fluid, it causes oxidation to occur at a more rapid rate, and oxidation in these fluids lead to an acceleration in the acid number, and unfortunately in this fluid the acid is typically phosphoric acid, which is pretty aggressive.
Everything oxidizes. So, when we're dealing with any fluid, they're all going to oxidize. Phosphate ester, it's just when it breaks down, when it oxidizes, that acid is a major problem, and it tends to be our focus. So we're going to, in order to maintain that fluid, Richard pointed out that it is, if you maintain it properly, it's a really good fluid. And one of the reasons why it's used so much is it's a very pure base stock without a lot of additives. So if we can keep it in like a narrow window, in a narrow range, the fluid will last a really long time and not cause a lot of problems. The acid that Richard's talking about, that's our primary thing that we're going to be concerned with, because it causes so many issues if it gets out of control. And once it gets beyond a certain point, it's very cost prohibitive and very difficult to bring it back. So our goal is to keep that fluid as close to pristine or new condition as we can. The fire resistant is why they use it. And the fact that it's, I guess they consider it self-extinguishing. So if it catches on fire and you take the heat source away, it'll go out. But we have to keep in mind that acid is our biggest concern. Now, one thing I'll point out, though, everything oxidizes. We're oxidizing sitting here. All fluids have their issues. For every good characteristic you get, there's going to be a trade-off. So obviously we're not oil advocates, but we do see this one a lot, and we can maintain it. So Richard was talking about water. The water accelerating the oxidation, I think that's a good point where we can talk about putting headspace dehydrators on it. So if we're going to go in, we're going to maintain this fluid. Obviously we're going to deal with dirt. We want to keep particulate at a minimum because this is still a hydraulic system.
Correct.
So we're going to manage the dirt. We want it. Everything we say about every other hydraulic system, every mineral oil system, applies here. If we keep the dirt down, if we put good quality filtration in, then the components are going to last longer. So for us as Hy-Pro guys, that's a given. We know we're going to get the oil clean, but we need to make sure we talk about it too, so that people understand that, okay, we have to keep it clean. To Richard's point, keeping the water under control. So now this fluid is way more vulnerable to water contamination than other fluids, and it's pulling water out of the air. So you don't even have to have a cooler leak or something like that. All you have to have is high humidity.
Well, not only out of the air, this fluid can pull moisture off of a desiccant breather bead. I mean, a desiccant breather can be a feed source to this fluid for water.
So we have to manage that. So, like I said, a given for us is we're going to handle the particulate. We know we're going to handle that. But sometimes we have to educate people. So we start talking about water. Well, if this oil can actually pull water out of a breather that's designed to keep the oil dry, how do we address that? So that's the next thing we're going to look at, right? We're going to look at, all right, we want to keep this fluid dry. And a way to do it is to insulate it from the environment where it would get the water, right?
Correct.
So that's where we start talking about headspace dryers.
So we make a vacuum dehydrator, but we recommend a headspace dryer because we're looking out for the customer and the upfront cost. They can both work, but the headspace dryer is really effective with phosphate ester.
Yeah, the headspace dryer is very, very effective as a maintenance item. Now, if the customer had a cooler leak or something where there was a really high ingression rate, we would talk about another technology. But like you said, what we want to do is provide the most cost-effective solution that's going to give the best results. Same thing that we talk about with filters, we're going to talk about which technology is the most appropriate for your application. The thing I really like is that in our offering is we have a headspace dryer that has a nitrogen generator. So we talked about water accelerates oxidation. Well, oxidation is a reaction that takes place in the presence of oxygen. So if we can keep the oxygen out, if we can keep the water and the oxygen away from it, now we've drastically reduced the rate of oxidation. So when we put dry nitrogen on the top of that, and the way to look at it, if you have a reservoir, there's always what's called a headspace in the top of it, right? And what that headspace allows is as actuators move in and out, you have to have room for the fluid to move up and down. Well, in that headspace, you have air. If there's a lot of humidity, the fluid's going to pull that in. So what we want to do is get it dry. Now, an interesting thing is, things are always moving. You're either on one side of equilibrium or the other. You're on one side of a saturation point or another. So if we put dry enough air in there, not only are we keeping it from pulling water out of the moisture into the oil, we can actually pull the water out of it. So that's why we call it a dryer. We're not just insulating or protecting, but we're actually pulling the moisture out. Well, if we can remove the oxygen, then it doesn't have anything to react with. You put nitrogen in, which is an inert gas that doesn't react well. There's nothing for the oil to react with. You drastically reduce the rate of acid production.
Correct. I mean, like you said, everything's going to oxidize when it comes to lubricants. The three things that accelerate the rate of oxidation is dirty fluid, wet fluid, and hot fluid.
And just for clarification, what you mean by wet fluid is the presence of water in the oil.
Correct.
Yeah, that's a good point because we do say wet oil or dry oil, and some people do get confused.
Well, on planet Earth, I think we talked about this when we were sitting around talking about water the other day. I don't know, which I primarily work in the southeastern United States. It's pretty humid down there. I've never seen a true sample with a Carl Fisher that shows zero water. Water's always present. It's just a matter of whether it's dissolved or whether it's free. In the case of any lubricant, by controlling water or decreasing the amount of water in the fluid within reason, you decrease the rate at which it oxidizes. On a phosphate ester fluid specifically, when the water content exceeds 500 parts per million, the rate of acid production increases exponentially. It's a curve. It's not just a little straight line on a graph that, hey, we went from 400 ppm to 700 ppm of water, so the graph changes just a little bit. It's actually a parabolic curve.
The classic hockey stick.
Yeah. And in that scenario, you're beginning to oxidize the fluid, and when this fluid oxidizes, you get phosphoric acid, and then a lot of other things can go crazy. So in dealing with a phosphate ester EHC type fluid, my opinion is deal with water first. Once you have water under control, then it's easier to get everything else under control.
Well, let's talk about the other things we do. So we have a really good way of keeping water under control with a headspace dehydrator. Ideally, if it's not an enclosed environment where you're concerned about nitrogen, we put the nitrogen generator on there. So now we're pulling the water out, we're insulating it from oxygen. Let's talk about the other thing is, okay, so we've got that under control. We're dealing with particulate. Then one of the other factors, because there's two more that I would consider, would be dealing with the oxidation byproducts themselves or the acid.
Years ago, when a lot of these systems were first built, they used a medium called Fuller's Earth to remove the acid from the fluid. Because Fuller's Earth itself is basically a clay product, some of that clay leaches into the fluid as a particulate. And for that reason, and again, this just goes back to the way of thinking back in the early 60s, a 10 micron cellulose filter element was put downstream of there, and it was called a polishing filter. But that polishing filter's sole purpose was to capture the particulate that the Fuller's Earth actually injected into the system. But they did that because they have to remove acid. If this fluid is left unchecked, like we said earlier, the acid number will get out of control. At that point in time, you have all kinds of system issues. There's another medium called activated alumina that's on the market now. It's a little bit better than Fuller's Earth in some degrees, but in other degrees, if you look at some of the activated aluminas, it'll flat out tell you do not use this in used fluid, but it doesn't define what used fluid is.
I think my assumption would be in service, but you're right, it is a gray area.
It has had situations where it's caused some pretty severe gels to form within phosphate ester fluids and EHC systems. Of course, that leads to filters blinding off, valve sticking. We use a medium called ICB resin for ion charge bonding. It's very similar to the resin that we use to remove oxidation byproducts out of turbine oil for varnish, which, if you think about it, oxidation, and we discussed this in varnish, we can discuss it again now briefly. Oxidation is nothing more than a loss of an electron in the presence of oxygen. You get a polar compound, slightly positive charge. In this particular fluid, most often oxidation always trends towards an acid, which is why we're really concerned with acid number. And we just use a more aggressive resin to remove the acid and other dissolved polar compounds out of this fluid.
Well, I think a couple things are important to point out about that resin. The two that you talked about, the Fuller's Earth and the activated alumina, they're alkaline, so they're trying to neutralize it that way, and they introduce things in that you have to filter out.
Correct.
And one thing that what we're using, it's considered ion exchange. So the term is ion exchange, but I like that we call it ion charge bonding, because when you hear ion exchange, it sounds like you're taking something out and putting something in. You're exchanging it, and you're not. You're literally giving that charged particle something to stick to. So the term's adsorption with a D, but there's nothing going back into the fluid. You don't need a post filter. There's not an exchange. You're just pulling these particles out, and that in itself, I think, is a really big benefit. There's not something going back in that you have to deal with. When you look at these other methodologies, some of the mineral salts, the things that come out that can leach out, can actually accelerate the oxidation and acid production. So you have these technologies that, if you kept it in a very, very narrow window, worked okay. They would take the acid out. The problem is, if the acid level got too high, then you start leaching these mineral salts out of the product that you had to keep the acid out, which accelerates acid production.
Right.
So a lot of the bad reputation this fluid had was because of the technology that was available to condition it and to maintain it, and people not really paying attention and keeping it in that narrow window. So one of those, I think one of the greatest advantages of going to ion exchange or ICB is that you're not worried about something coming out that make things worse. If my job is to clean up your fluid, I'm doing it to make things better. If there's a chance of what I'm doing is going to make things worse, then we really need to think about what we're doing. And that's one of the things that's exciting about this technology. The other thing, besides accelerating acid production, if you get too high and start leaching these things out, the alumina silica, those particles that get leached out are harder than hardened steel components. So now you have a very highly abrasive component. That's what you make sandpaper out of. Once again, if we can put something in the system that you don't have to worry about something coming out, that its only thing that it's going to do is improve the performance, I think there's a peace of mind that a customer can have. That there's one less thing for them to worry about, besides the fact that it's going to perform and get the acid out.
Right.
So on the water aspect, we talk about, I'm going to product name drop, TMRN2 for nitrogen separator. We're taking nitrogen going across the top like you referred to. A lot of people have issues with desiccant breathers lately because they expire and cost money. I get that. But this is one application where we actually do recommend that there's a desiccant breather on the other side, because the operator or the technician, as they walk by, they can see as the air flows through the reservoir and exits through the desiccant breather, we're going to keep that breather dry. So that's a visual to be able to see that the fluid is being maintained dry. I wanted to point that out because there's a lot of people that are starting to kind of migrate away from desiccants if not properly applied. But that's one application where we really do recommend it. And when it comes to water, we need to remember with the phosphate ester that there's actually two areas where we can be in a bad situation, but high water is much worse. So we definitely want to get control of the water, because if you have high water, you have a very aggressive phosphoric acid that's going out into the system and either etching surfaces or starting to attack seals. But we also do want to mention that there is a potential issue for this one fluid if it's too dry.
Yeah. Years ago, EPRI, the Electrical Power Research Institute, released a study on maintaining phosphate ester fluids, and it surprises me that there is not as much knowledge of that document today as I would expect, because it's not uncommon for me to go into power plants and look at their oil analysis and look at their upper limits, lower limits, or as some people call them, target values, and they're well outside of the realm of what EPRI actually recommended. And when it comes to water, EPRI recommended a water content at or below 500 parts per million, which is the number that we recommend as well, because it's in line with that particular study. They also recommend the acid number be below 0.1. But it's not uncommon to go into a plant and look at their analysis, and they'll have a 0.2 or a 2000 ppm value for water, and they'll have a 0.2 number for acid. And like we mentioned earlier, if you're above 500 ppm, acid is being produced at an accelerated rate. If you're using some of the older technologies, Fuller's Earth or activated alumina, as the acid is removed, metals go into the fluid. And then another interesting thing about this fluid has very poor air release properties as it is. When you get dissolved metals in this fluid at or above around 10 parts per million, excluding obviously phosphorus because it's a phosphate ester, the actual air release properties are pretty much annihilated. And at that point in time, you begin to have pseudocavitation, or some people call it microdieseling, where you're actually causing air bubbles to form in the fluid at the inlet side of a high pressure pump. And then on the discharge side, discharge pressures in these systems are 12 to 1800 psi. Those bubbles implode. That causes damage to the pump in and of itself, but it also causes damage to the fluid. It'll actually burn it.
Yep.
And you mentioned earlier, what are the things that accelerate oxidation? One of them was heat. So you're accelerating oxidation. So you have something that you put in the oil to remove acid to help maintain it. It releases mineral salts or metals into the fluid that hurt air release, which increase the likelihood of heat, which accelerates acid production. Any of these variables that you can take out, you're going to have a better life with the fluid.
Yeah, it's not a surprise to me that a lot of people hate this fluid. But again, if you pay attention to a couple of variables,
It's easy to control.
the fluid should last lifetimes, because again, there's no additives in this stuff to really come out.
That's a good point to bring up. That there's no additive package to be depleted, and so a lot of times the lubricant supplier or manufacturer would say, based on additive package or contamination, there is no additive package. So if we keep this in spec, theoretically, if you don't leak it, it should last for a very, very long time. So, and then just to circle back to one last point I want to mention on the low limit on water is we have a 200 ppm low limit. We have found, and we haven't done extensive testing because, we've been very busy with other projects, but we have a strong belief that below 200 ppm, phosphate ester turns solid black due to oxidation or some sort of an event on the microscopic level, electron level. Carbon buildup is occurring. It's not going to affect the performance of the fluid, but it's going to look very dark and very quickly. I had a customer that replaced their old fluid with new fluid after it had been cleaned, and within about a 30-day period, run it at about a 100 ppm, they had very dark fluid. It was still functional, but visually. Can that lead to other things? So we do have a lower limit as well, knowing though that the upper limit is more critical. That is the
Yeah, I think the important thing to point out on the lower limit is our information on it is anecdotal, but it's a significant amount of field anecdotal. That if we're trying to keep this fluid operating at its best, this fluid being able to do what it was designed to do, keeping a little bit of water in there does seem to give it the ability to do that. And we're not sure if it's air release, we're not sure what exactly is going on, but it does seem like it can get too dry.
Yep.
But if the fluid turns dark from microscopic carbon, we do have a solution for that. So you can't remove that mechanically, at least not even down to half micron. I've done some testing with that, and even a half micron filter won't remove it. But we do have an electrostatic filter that will remove that. And what's interesting is those electrostatic filters, there are other companies that are trying to use that for other applications where they don't work. This is the one application where electrostatic makes sense, and that's removing submicronic carbon out of the fluid.
So to review, water is the number one thing that we like to talk about with our customers. That is the most important aspect we need to get control of now. Then we can look at the acid scavenge kidney loop on a system and say, okay, your acid scavenge media, if it is Fuller's Earth, ion charge bonded resin technology has 7 times capacity. Every once in a while we'll hear a customer say, I can't get control of my acid. Well, if they're using Fuller's Earth, that cartridge can expire very fast and then have to be replaced very fast. So if testing isn't done consistently with trying to recover a system with Fuller's Earth, that's why. Put a new cartridge in, doesn't do anything.
Well, and above a total acid number of 0.1, you start leaching those metal salts out and you're accelerating acid production. So if they're above a certain point with the Fuller's Earth, it's very, very difficult to get it back in spec. And
Yep.
you'll see people ordering skids of Fuller Earth cartridges to try to bring it back in spec, having to change them so fast.
Takes 7 canisters to equal the amount of acid scavenging as one ICB canister, just to put it in perspective.
Mm.
So the TMR N2, a headspace dryer, exit through a desiccant breather. We have our water under control. The acid scavenge loop, we have phosphate ester going through the ICB, so resin. And then next step, you are going to still have a filter housing because that's the way it's always been. So we recommend, just like EPRI recommends, a very high efficiency filter element there to have an effect on the whole system. It seems to work.
Yeah, if the filter housing is large enough, I like to use our VTM media.
Which is approximately where in micron?
It's rated at around a 0.9 micron.
0.9.
If the housing is not large enough, and some of the newer steam turbines at combined cycle plants use a really, really small polishing filter, and VTM is just, the housing's too small for that. So in those cases, at the minimum use, what we would call our 3M media, which is Beta 4 Subcia 4000, or if in most cases I try to at least use 1M.
Well, that does a very good job.
Well, and in cases where it's just not practical, we can do an offline skid that will take care of everything. So we've got skids that we can put the dryers on, we can put the ICB in and the VTM.
And a lot of our products are, or most of them are, a customer request. We have a customer request. Can you build us a complete new acid scavenge loop on a skid with a headspace dryer like you're talking about? We can do that. It's very rare. Mostly it's an upgrade of an existing system, but we do have that capability. So we can mix and match as we need to. Okay, so that's great on phosphate ester. But just to go back to the lab report before we move on, what are the things that you want the customer to look at every time they look at the lab report on phosphate ester?
They need an acid number of below 0.1.
0.1 is the limit.
Always look at viscosity, no matter what the fluid is.
Always look at
Always look at
viscosity. Yeah.
So if you're way out on viscosity, nothing else is really going to matter. It's so.
And that is the number one factor, so that is important.
So you want your water content to be below 0.05% by weight or 500 parts per million.
Yep.
Since most of these systems that we encounter are include servo valves in the 1,500 to 2,000 pound operating pressure range, your upper limit for ISO cleanliness code should be 151310 or lower, preferably lower. And then the other thing I guess we would be remiss for not touching on would be the MPC data. A lot of labs report the delta E value when they do MPC analysis on phosphate ester fluid. I can't tell you how many times I've been contacted by a power plant thinking that the whole world's coming to an end within their system because their MPC delta E is in the critical range. But although MPC delta E is the standard for looking at varnish potential in a mineral-based, say a turbine oil, if you're going to apply MPC to a phosphate ester fluid, you need to look at individual values, the things that make up the delta E. You need to look at delta L, you need to look at delta A, and you need to look at delta B.
Just real quick for people who may not know, that's MPC is membrane patch colorimetric, and essentially what it is, without getting into all the specifics of the test, you're using a solvent to drop out soluble contaminants, and they're coming out on a patch. And what you're doing is you're looking at a level of things that you wouldn't necessarily be able to remove mechanically, but that can cause damage. So it's looking at how dark a patch is compared to a new one, and it's giving you a look into the soluble contaminants that are in the fluid. Sorry to interrupt. Not everybody knows what that
that's
is.
a good point.
But delta A covers half of the colors in the rainbow. Delta B covers the other half. And then delta L is the white to black scale. And without getting nerdy, there is a formula that where you take those three values and extrapolate what is actually reported as delta E. But a delta E value on a phosphate ester fluid will, the vast majority of times, come back as critical, which can cause you at the plant to be chasing quote-unquote ghosts. So if you do MPC analysis on your phosphate ester fluid, and we highly recommend that you do in fact do so, make sure you're using a lab that will report the components of delta E. You want to look at delta A and delta B, and delta L is three independent values. And then your upper limits would be delta L should be below 20, and delta A plus delta B should be below 10.
And what that tells you, those two color breakdowns that you're talking about, one is going to tell you about oxidation byproducts, and the other one's going to tell you about carbon from things like microdieseling and other events. So by being able to look at the two, not only do you know what the problem is, but you know how to attack the problem, and you also know how critical it is. So if it's mostly carbon, yeah, that's a problem and you need to deal with it. If it's mostly oxidation byproducts, that's going to cause you a lot of other things. And they have different technologies to approach them. So we were talking about electrostatic for the carbon, and then we have the resin for the oxidation byproducts. But it really gives you a window into what's going on, but it also really helps you develop your strategy on how to address it, and it helps you know how quickly you need to address it.
Correct.
That's a really good point. And so that's phosphate ester in a nutshell. Easy to manage, but you do need to look at the details. So I'm glad that you brought that up about the L delta A plus B. Just to reiterate, like you said, it's either going to be a high temperature or an oxidation event, and we're trying to figure that out, basically. And we're trying to also identify the color of the patch.
Yeah, at the end of the day, the best oil analysis should do more than just tell you the condition of the fluid. And with those particular values, use an MPC analysis in that way with phosphate ester. When you do have an upset condition, it can help lead you to the actual cause of that upset, so that you're not just spending a lot of money with a company like Hy-Pro that, we can remove this stuff. But if you know from where it's coming, you can attack the cause of it to decrease your total cost of ownership again. You want the fluid to last, and you want your filtration to last as well, to protect all the components within the system.
Well, and that really touches on one of our goals. When Hy-Pro first got started, our goal was to make the equipment last longer. But what we've learned over the years is we can also make the oil last longer. And so, especially with phosphate ester, we have the ability to not only extend the life of the controls on that turbine, but we can also extend the life of the oil, which is critical and gets into a whole nother set of savings.
Yep.
Yeah, and this fluid is not inexpensive.
No.
This fluid is in the $65 to $75 per gallon range. So a 55-gallon drum of this stuff is pretty costly.
All right, thanks, guys. I think we covered it well.
This has been the Hy-Pro Podcast. For more information on any of our products or services, you can find us on the web at www.hyprofiltration.com. Remember, please lubricate responsibly.